Hello, in this video we're going to have a look at the quotient rule for derivatives. And just to remind you that a quotient is the result from dividing a couple of things together. And in this instance we've got a function f of x which is defined as u of x over v of x. So u of x is the a mini function and we're dividing it by another mini function. And then we have the quotient rule here. And again, I've simplified it to make it a little bit more palatable in notation. And we've got f dash equals u dash v minus uv dash over u squared. And the astute amongst you might notice that this is exactly the same format on top as the product rule, except with a minus instead of a plus. And that's why I got you to learn the product rule in this order. Other textbooks and other sources will have these two and these two swapped over, which for the product rule doesn't matter because, you know, when you add two things together, it doesn't matter which order you add them. But subtraction is not commutative, which means that this minus this is not the same as the other way around. So you must have it in this order. And that's why if you've been practicing in this order with the product rule, it's just a matter of putting a subtraction in the middle for the quotient rule and then dividing it by the square of the oh dear, I've got a problem there. Square of the v squared, not u squared there. You can see I've got a v there, and I've just done the wrong notation there, so I'll fix that up now. Like a bit of a doofus that moment there. You know, if I was actually and anything like a professional, I'd redo the video, but what the hey, we'll just leave it at that. And you can see here I've got the quotient rule as a fairly straightforward extension of the product rule. It isn't too hard to explain why, but I'll put it into a separate bonus video for those of you who would like to see it happen. It's a nice little algebraic exercise to do. It might help you understand where the quotient rules come from and therefore utilize it a bit more readily. It's not essential for you to know how the quotient rule works. It's just necessary for you to know that it does work and for you to apply it consistently, correctly over a series of different problems. But look, we're here not just to be rule followers, but also to understand what we're doing because that develops further and deeper understanding of deeper concepts. So although it will be a bonus additional video, I do encourage you to watch that extra video because it really will help you out. Okay, let's have a look at an example of the quotient rule in action. And I'm going to do what I did with the product rule, and that is just start off with a problem that we have done previously using other techniques, and I'm following through with it. So we've got f of x equals x squared minus 4 all over x plus 2. You can see I've factorized the top using difference of two squares, and then I've cancelled out the x plus 2's here, which leaves me with x minus 2. So I haven't found the derivative yet. That's just what f of x is equal to. It's equal to x minus 2 with a caveat that x can't equal negative 2 for reasons that you can probably see there. So the derivative of that is just 1. Now let's have a look at doing that using the quotient rule. So we've got f of x equals x squared minus 4 over x plus 2, and we are going to use the same idea as we did in the product rule. I start with u, which is x squared minus 4. Then I work out u dash, which is the derivative of it, which is just 2x. Then I've got v, which is the bottom, x plus 2, and v dash is therefore equal to just 1. Okay, simple derivatives there. So that means that f dash of x is equal to, okay, so inside then outside. And again, remember, order does matter. So we've got 2x outside of x plus 2 minus, and now I'll do the outside. I've got v dash equaling 1, so it's just minus x squared minus 4 here. Okay, all good. All over the square of v, which is just x plus 2, all squared like so. Okay, if we left it at that, it would not be as simple as we can make it. So let's just do a couple of expansions and see where we get. So it's going to be 2x squared plus 4x. So that's this bit expanded. And then we've got x squared minus 4, which has got a minus at the end, at the outside of it. So that's just going to be minus x squared plus 4 all over x plus 2 all squared. Okay, now I'm going to simplify that. So that's going to be equal to 2x squared minus x squared is x squared. And then we've got a 4x, no like terms there. And we've got a plus 4 there, all over x plus 2 all squared. And you might want to pause it and think about it, but that numerator can be factorized. It is, in fact, pause the video if you want to figure it out for yourself. it is in fact a perfect square. We've got an x squared on the left there, we've got 4 on the right, which is 2 squared, and in the middle we've got 2 times x. So we've got the exact right notation for a perfect square. If that doesn't make sense to you, may I suggest that you go back and practice those fundamental rules, because all of those basic building blocks of algebra are what makes you being able to tackle more complex problems, more straightforward activity there. So you've got x plus 2 all squared on top, x plus 2 all squared on the bottom, cancel, and we're left with f dash of x equal to 1, which is the same as we got on slide 2 there. So there you go. The quotient rule did give us the same solution. Now again, let's see if I don't get any questions about this. Would you use the first example in blue there or the second example there using the quotient rule? Anyone who uses the quotient rule for this needs their head read. It needs to be the first way, isn't it? It's a lot faster. So again, I'm just reinforcing the idea that when you're confronted with a problem, what you should do is say, what is the best tool for the to solve the problem in the most efficient way possible? Clearly, for example, 1, it is much more efficient to do a factorization, cancel down, and then find the derivative. In example, the revisited example 1 there, that was a much longer way of doing it, even if we got the right answer. So always step back, think about it, then start solving your problems. And, the more you do that, the more efficient you'll be, the faster you can solve problems, the more marks you'll get, etc., etc., etc. Lots of bonuses there. Okay, let's have a look at some examples which aren't so... you certainly, there's no shortcuts really for these ones here, I don't think anyway. Now, technically, I suppose this first one, there is a shortcut. We know what if y equals tan x, we know what dy by dx is. It's x squared x, right? But let's have a look at that in practice above proving it, I suppose. So we know that there's a trig identity which says that tan of x equals sine of x over cos of x. So let's use that identity plus the quotient rule to prove that the derivative of tan x equals sec squared x. Okay, so we start off with our usual. U equals sine of x, therefore u dash is equal to cosine of x. V is equal to cosine of x, therefore v dash is equal to negative sine of x. There we go, and then I'm just going to pair them up for my derivative. Dy by dx is equal to, inside cosine x times cosine x, that's cos squared x. The outside, I want to do a couple of things at once here, so I'll verbalize it. So if you get confused, just ask me in class to explain. Sine of x times minus sine of x is negative sine squared x, but the quotient rule says I'm taking away, so that taking away a negative is the same as adding. So I've got sine squared x here, all over the square of cos x, which is cos squared x, beg your pardon. Now, up the top there, did you notice what that is? Cos squared x plus sine squared x. It's the Pythagorean identity, and we know that sine squared plus cos squared, or cos squared plus sine squared equals 1. So we end up with 1 over cos squared x, and that's equal to sec squared x, which is what we would expect. So there you go. We've just done a proof, if you like, that the derivative of tan of x is sec squared x. There you go. Example 3, d by dx of e to the x divided by the square root of 1 plus x. Now, I am going to do this fairly quickly, okay, doing a few shortcuts here, hoping that you're getting pretty quick on using chain rule and all that kind of stuff to make it short work of this. So u is equal to the top, which is e to the x. So u dash is just equal to e to the x as well. No chain rule there. V is equal to the square root of 1 plus x. And knowing a little bit about how functions work, I'm going to go straight into power rules there. So 1 plus x to the power of a half. So v dash is equal to a half. 1 plus x to the minus a half. No chain rule, actually. And then I'm just going to notate this as a negative power becomes a positive power, but on the bottom of the fraction, a half is actually a square root. So we end up with 1 on the square root, 2 root 1 plus x, like so. So that becomes that one. And now we just need to put it all together, and we're going to have to be a bit squishy to get this going, but let's see how we go. So d by dx of that lot there must be equal to, okay, so inside and then outside. So we've got e to the x square root of 1 plus x. There we go, that's the inside. Minus, and now the outside, e to the x multiplied by v dash, which is this thing here. So that ends up being over 2 root 1 plus x. Doing a fair bit of shortcutting here with my steps here. So again, if you're getting confused as to how I'm going from one step to another, just ask in class. And this is all going to be all over v squared, which is the square root of 1 plus x, all squared like so. Okay, so that is that one done. And if I simplify this a little bit, I'm going to have e to the x, and I'm going to have the square root of 1 plus, oh, hang on, let me go one more step. This, I'm going to find a common denominator. So I've got 2 root 1 plus x. There's no denominator here. So effectively what I'm going to be doing is I'm going to be multiplying e to the x root 1 plus x by 2 times root 1 plus x to get my common denominator, of 2 root 1 plus x. So that's going to give me 2 e to the x, and watch what I do here, 1 plus x. Because when I multiply the square root of 1 plus x by the square root of 1 plus x, it'll just leave me with 1 plus x. Minus e to the x all over 2 root 1 plus x, like so. And then what happens to my denominator? Well, my denominator is root 1 plus x all squared. Because I'm squaring a square root, effectively undoes each other, so I'm just left with a 1 plus x. And I'm going to be going divided by 1 plus x here. Okay, let's bring it all together in slide 7. So we have e to the x, and that's a common factor, right? So let's take that out, and inside I will have 2 outside of 1 plus x. So that's going to be 2 plus 2x, and then minus 1. There we go, with that common factor of e to the x and an expansion there. As I said, I'm doing a few steps at once here. 2 outside of 1 plus x. So that's what's happened to this divided by 1 plus x here. Becomes multiplied by 1 over 1 plus x. 2 outside of 1 plus x, square root of 1 plus x. There we go. Quick simplification. So that's equal to e to the x, 2 minus 1 is 1, so 1 plus 2x, all over 2 outside of 1 plus x, square root of 1 plus x. And I think that's about as simple as we can make it, I think. There's quite a bit of algebra there, and that's what makes this kind of question an A standard question. Finding the derivatives, it's a little bit tricky, but it's not too bad. But it's what happens after we've found the derivative is what makes it tricky. By the way, I noticed in class a number of people, even if they're listing these things here, sometimes they're listing them across the page instead of down like I do. Sometimes they're not putting these square brackets in like I do. Look, that's fine. If that's what you want to do, whatever floats your boat. However, I find that by getting into the habit of doing these little pictorial things here, by listing them down in order and bracketing them up like this, what you're doing is you're chunking down your thinking into small pieces, and then when it gets into high pressure situations or when it gets more complex, your reflexes take over and you get through this, and the actual visuals here stop you from making silly mistakes as you go along. So in my experience, laying it out like this allows you to work on higher order thinking, knowing that your reflexes here will cause you to, follow the right flow, I suppose. And then, it all comes together, in my opinion. Okay, let's have a look at example 4 here, my second last example of this long video. Find the exact value of the gradient at x equals 4, given, I didn't write the function in, given that f of x is equal to e to the x on sine of x. Lovely jubbly. Let's have a look at this. So this is just the gradient that we need to work out. So we just start off in the usual manner. We say u is equal to e to the x, therefore u dash is equal to e to the x. V equals sine of x. I haven't done much chain ruling, have I? V dash is equal to cosine of x. Okay, so therefore f dash of x is equal to, okay, inside then outside. So we've got e to the x sine of x minus e to the x cosine of x, like so. And so, all over sine of x squared. So sine squared x. Okay, that's that done. Now I'm just going to take out a common factor of e to the x I can see there. Plus, I'm now going to evaluate at x equals pi on 4. So I'm going to say f dash of pi on 4, watch me do a couple of shortcuts here, is equal to e to the pi on 4 outside of the sine of pi on 4 minus the cosine of pi on 4 all over sine squared pi on 4. Now, in my little brain here, I can see where this is headed. So it looks complicated, but it actually gets easy pretty quickly. And just keep in mind, regardless of what happens in the answer here, it says exact value. So in a it doesn't matter if it's non-calculator or calculator section, if it says exact value, that means that if I end up with an answer with e to the power of pi on 4, I'm going to leave it as e to the power of pi on 4. I don't care what it is. I can probably have a bit of a guess at what the rough value of it is, maybe knowing that e is 2.7. And what is pi on 4? About a quarter of 3. So, you can sort of work out that's about 0.7 something, 0.76 maybe. So you can sort of have a sense of what the number is going to be, but it doesn't matter in terms of the answer. Exact value means we're just going to leave it as e to the pi on 4 and whatever else. But here and here and here, we do know what these values are, the exact values are, so we should evaluate that. So that's equal to e to the pi on 4. And we've got sine of pi on 4, which if you look at your information chart or from your memory, you should know is root 2 on 2, minus the cosine of pi on 4, which actually also is root 2 on 2, all over sine squared of root 2 on 2, which means it's sine squared of sine squared pi on 4, which is going to be root 2 on 2, sine of pi on 4, all squared. And I'll just squish it in here so it's in the one page here. Now, here's the thing. I didn't actually mean this to be so simple in the end, but we can see here I've got root 2 on 2 minus root 2 on 2, which is equal to 0. That'll make this whole top number 0. This bottom number doesn't matter what it is, it's all 0. So it ends up with the gradient at that point is actually f dash of pi on 4 is actually completely equal to 0. So it must be a turning point. Oops, didn't mean for it to be a turning point, but there you go. It's a turning point. P.S. Just a mindful that if this wasn't 0 up here, root 2 on 2 all squared would actually be 2 on 4, which is equal to a half, just FYI. Okay, let's have a look at our final example, and this will do for this video here. F of x equals e to the 2x over cos 2x. So there's a little bit of chain ruling here. So here we go. And it says find the normal of the following function of x equals 0. So it's going to be a bit scary, isn't it? Okay, so let's start off with our normal process, and that is if I need to find the normal, I need an x and a y coordinate. I've only been given an x coordinate, so let's substitute in the x coordinate to find the y coordinate. F of 0 equals e to the power of 2 times 0, so it's e to the 0 over the cosine of 2 times 0, which is just cos 0. Okay, that's not a problem at all. E to the 0 is 1, and cosine of 0 is 1, so we've got 1 over 1, so that whole thing is equal to 0. So we've got the point 0, 1. Also off to the side, I'm going to do my u's and v's here, ready for the next part. So we've got u is equal to e to the 2x. So u dash is equal to, chain rule, e to the 2x is e to the 2x, and the derivative of 2x is 2, so it's going to be overall 2e to the 2x. V is equal to cos 2x, which means that v dash is equal to, the derivative of cos is negative sine, so we've got negative sine of 2x, and the derivative of 2x is 2. So I'm going to end up with negative 2 sine 2x. So again, with practice, I can see where this is headed. So, I didn't go multiplied by negative 2 or anything like that because I knew where it was headed. Okay, having done that, I've got my inside and my outside, so I'm now ready to find my derivative. So I've got f dash of x is equal to, here we go, we've got 2e to the 2x cosine, oops, don't know what I'm writing there, cosine of 2x. Okay, so that's the inside minus the outside, which is, I've got a minus 2 there, so my minus 2 is going to make this a plus and then a 2. So minus 2 is plus 2. And then I've got e to the 2x, and then I've got sine of 2x. Okay, all over the square of cosine of 2x, that's going to be cos squared 2x, like so. So that's my thing. Now, looking ahead, I don't think I'm going to worry about simplifying this, even though I can see a common factor of e to the 2x. I'm just going to go straight for working out what the gradient is at 0. So f dash of 0 here. And I'm going to figure out what that is. So that's going to be 2e to the 2 times 0, so 2e to the 0, cosine of 2 times 0, which is 0, plus 2e to the 0 sine of 0, all over cosine squared of 0. And I can see lots of zeros here, which are going to simplify quite handily. So this is going to be 1, 1, 1, and this is going to be 0. So effectively, this term disappears. So I'm going to have 2 from my first term there, plus 0, because sine of 0 is 0, all over cos squared of 0, which is just 1 squared, which is 1. So I'm going to end up with 2, which is going to be my tangent gradient. Okay, well, we were asked to find the normal, so therefore the normal is going to be negative 1/2. Okay, so there's my gradient for the normal. So I've got my xy coordinate, I've got my normal. The rest of it is pretty straightforward. I've got at the moment y equals negative 1/2 x plus c will be my normal equation. And at 0, 1, I'm going to have 1 is equal to minus 1/2 times 0 plus c. So c is equal to 1. Therefore, the normal is y equals negative 1/2 x plus 1. And I'm done. Okay, so there's a bunch of examples there. Just wanted to be thorough enough with lots of different kinds of things here. So hopefully that was sufficient for you to have a bit of an idea about the variety of problems that you can come across. It's your turn now to do as many problems as you can using the quotient rule so that you can be well practiced at using it. But don't forget, whenever you come across a problem, you should be asking yourself, is this the right tool? Should I be using the quotient rule? Can I do some simplification first before I use the quotient rule? Or is there another rule I can use which is simpler, like the power rule? Always ask yourself the question first. Good luck.